short final lecture to kind of frame the entire class. Thanks for taking Biological Statistics in R. As arguably the most powerful tool we have developed in science, and I think I would stand by that argument. There are numerous traps that we could slip into, and therefore I want to take a little bit of time as sort of a last cautionary statement. Personally, I use statistics constantly in all the way different shapes and forms. I got my master's degree intentionally so I could develop out more quantitative scores, and then I've just continuously added to that throughout my career. I'm by no way the most quantitatively inclined researcher you'll meet. Nope. Even on this campus, there are many people who are much more adept than I am. But what I'm able to do, and this is what our goal is for you, is to be able to use these tools effectively for addressing the questions that you have. And as a scientist, that strikes me as the most important thing. We have questions, and we are interested in finding answers, and we're interested in finding answers that are consistent with the evidence and therefore represent what reality actually is. All right, so let's get started. This last piece of information comes and is modified from Matulsky, chapter 45. And if you haven't read Matulsky, I do highly, highly encourage it. I think this cartoon is fantastic. I used to think correlations implied causation. Aw. Then I took a statistics class. Now I don't. Aw. Sounds like the class helped. And the answer is, well, maybe. That's good. All right. So our first concern is this over focus on p-values, and this is something that, as we've talked about throughout the semester, is really the first step for many of the tests that we utilize, especially when we're utilizing Popperian statistics. And p-values are important to sophisticate, but an acne p-value is less than 0.05. That settles that. Female. I hear it's only certain colors that cause it. Scientists. But Minecraft. We found a link between purple jelly beans and acne. Oh, we found no link. We found no link between brown jelly beans and acne. We found no link between pink jelly beans and acne. Found no link between blue and acne. Teal and acne. No to salmon and acne. No to red and acne. No to turquoise. No to magenta. No to yellow. No to gray. No to tan. No to cayenne. Oh, we found a link between green jelly beans and acne. No to mauve. No to beige. No to lilac. No to black. No to peach. No to orange. News. Green jelly beans linked to acne with 95% confidence. Only a 5% chance of coincidence. Scientists. This is p-hacking, and it's a form of p-hacking that is identified as HARC. Hypotheses after results are known. So one of the things you want to do is you really do want to think through the hypothesis before you do your research. You want to think about your hypothesis before you analyze your data. And there's always more than one hypothesis, and there's more than one question within the individual data set. Formulating your hypothesis after you have your data causes whole sorts of problems. Like in this case, we've likely committed a type 1 error, in the sense that you are always going to find eventually some realization if you continuously test out the data. And we've done a number of things to try to avoid this. One of the things is the type of test that you do. One of the reasons for a two-way ANOVA is you're looking at more than one variable at one time. In addition to being able to see the interaction term, you can also actually control for the variation that might exist between the variables you're testing. In addition, when we're doing our logistic regression, or when we do linear regression, it's very easy to create a model with more than one influential variable. This controls for this effect of repeated tests and the chances of committing that type 1 error. Then we have this problem, and this is the big one. It's called p-hacking. And this is analyzing without a plan and picking the tests that give you the results you want to see. And this comes from published data. And this shows you the frequency distribution of different p-values relative to the number. Well, remember, if a p-value is actually representation of a normal distribution, well, the first thing is this entire figure should be different. You should actually find more cases of 0.1 and fewer cases of 0.01. Now, arguably, we generally are testing questions where we expect to see a pattern, and I entirely get that. So that might just be reasonable because of how we set up our studies and the type of questions we ask. We're not asking questions at random. But do focus on this, and focus on the number of p-values that are just slightly less than 0.05. And the paucity, the infrequency of p-values that are just slightly greater than 0.05. This has to do with that inflexibility of this arbitrary threshold. The threshold has logic. It's roughly 2 standard deviations from the mean, and that makes sense to use that for our type 1 error. But when you see a pattern like this, what you're clearly seeing is a number of researchers who will do different tests until they can break that threshold. And then once they break that threshold, this is the group that's going to talk about why I found significance. Well, again, as a reminder, significance doesn't mean anything. It really doesn't. It's a qualitative statement that has to have some context. What a p-value less than 0.05 shows is you should describe the alternative hypotheses. What a p-value greater than 0.05 shows, you should describe the null hypothesis. One of the things about all the p-values on this table between 0.01 and 0.1 really identifies the case where you should describe possible patterns, possible differences, possible correlations. We should be very cagey when we get a p-value between 0.03 and 0.07, 0.08. The reason is we're talking about an absolute change. Either we see a pattern or we see a random pattern. Well, that threshold that describes that change is a fixed term, and a little bit below doesn't mean it's automatically a pattern. And a little bit below doesn't mean it's automatically random. Be cautious in how you interpret the p-value and use the p-value as only the first step. Be careful about misreading them. Failing to understand the null hypothesis is really dangerous. Many times the null hypothesis is the interesting biological phenomena. Many times the alternative hypothesis is the interesting biological phenomena. You have to pay attention to what that is in order to understand how to utilize the statistics. Failing to know what the p-value evaluates, and that's those cases where we just talk about there is a significant pattern. No, describe it. Provide context to it. Use it as a tool, not as an endpoint. And then this issue right here, ignoring p-values that are greater than 0.05. Well, those are meaningful. Random patterns are meaningful. Non-influential effects can be meaningful. We need to know them as well. Experimental design can cause all sorts of problems, and we've talked about one of them. And that's this issue between correlation and causation. You want to avoid over-interpreting observational studies, like the one we see right here, which describes the median income of individuals in 2011 relative to the likelihood that they voted for Rooney. It identifies it across 50 different states, and it's correlative, and it kind of suggests that there's a negative relationship. Poorer states were more likely to vote for Rooney, and richer states were more likely to vote, well, for someone else. And that's an observational study, and that's correlative, and it can be interesting, but we shouldn't overinterpret what that means. In addition, you should not overinterpret what experimental studies mean. Experimental studies have the con of always being artificial, and frequently, by controlling for causation, you get great insights, fantastic insights, but many times you will also get a very artificial response. You really ultimately need the combination of both of these, where individual observational studies provide that real-world situation, and individual experimental studies allow you to evaluate that causation. And then also be very careful about that change between interpreting individuals from groups. And this is a really nice example of that. These are representations of states. They're not actually representations of individuals within that state, and those can frequently be very different phenomena. It is highly possible, as it was in the case for this election, where individual states dates show this negative relationship, but when you actually looked at individual incomes, we see a positive relationship where wealthy individuals actually voted for Romney at higher rates. So be careful when you interpret at what level you're examining. And this shows that individuals and who they voted for. In addition, pay attention to the distribution of the numbers. One of the biggest mistakes people make is the obsession and over-reliance on central tendencies, means, medians, and ignoring the variability, confidence intervals, standard deviations, quartiles. In order to understand the overall patterns, you've got to pay attention to both sets of phenomena. Further, don't ignore the real distribution of the data. One of the things I definitely encourage you to avoid doing since the beginning of the semester, and I will always encourage this, is trying to recreate some sense of normality in the distribution. I see an argument for it in some cases, and there are some cases where there's a good argument for it. And one of the benefits of a factor analysis is it does create new variables that approximate a normal distribution. That is great. But there are so many different ways of doing analyses that trying to conform to tests and techniques that were developed in the 1930s, 1940s doesn't make any sense. Use modern statistics. Use modern approaches in order to address these problems where, when you use these modern approaches, you don't have to worry about normality. Further, don't immediately plunge into ranking data. Remember, ranked data is weird. It has that situation of uniform distribution. It changes the structure of the variation within the data. You got all of those weirdnesses that occur when you have tied ranks. I mean, it works, but it is weird. What I will strongly encourage, and what I've been encouraging, and I haven't actually seen it a lot in this class, use permutations. They are straightforward. They are clean. You do not have to test for normality. You can use things like a one-way test with coin. You could use things like AOVP with LM-Perm, and you could use Permaco. These are all packages that allow for permutation tests very easily, where instead of actually treating our data and forcing it to conform to a distribution like normality or uniformity, what we do is we use the distribution of our data, and then through resampling, randomize reassortments of that data, we can identify whether what we measured is extremely different than what we are randomizing. It's a great approach. And then last, and this is really kind of a great point to end on. Lying with stats is difficult. When a person knows what you are saying, when a person understands what you are saying with the data, it is very hard to lie with stats, because a person who understands data, understands stats, can easily hear what is being said, easily read what is being said, and identify where there is misinformation being present. However, and this is so critical, it is very easy to mislead the ignorant. So one of my goals with you this semester is to help you become more confident with statistical approaches, help you become more confident with numbers and distributions, and help us reduce some of our ignorancy. I have much to learn. I suspect after one class you still have much to learn, but thank you for a great semester.